I'm a retired physicist, a scientist emeritus from Fermilab. I worked there for 30 years. I'm retired now, so I'm an unemployed physicist, if you like. But I've had a great time so far and continuing my career. I was privileged to be part of the discovery of the two heaviest particles we know, the top quark and the Higgs boson. On the left, you see a picture of me in the Tevatron tunnel, where we discovered the top quark back in 2012 and 1995 that was, and then the Higgs boson was discovered at CERN at the Large Hadron Collider. That was in 2012. So in this talk it's in two parts really. One is about great women physicists and astronomers before Marie Curie, and Marie Curie was a transition, and then after Marie Curie. So a couple of quotes here. The times they are changing, hopefully. And the theme is about Nobel Prizes, because I'm using Nobel Prize winning scientists as a sort of figure of merit, but it's clearly not a figure of merit because it's so biased in favor of the male. I had a science column in a local paper before I moved here, and one column I did was called Girls and Young Women, Do You Like Physics? Do You Like Science? Go for it. And I put up here a link to these columns, which, especially in November 2018, was on that topic. So here's a question for you. For a period of 100 years, there was only one woman who won the Nobel Prize in Physics. Do you know who it was? Marie Curie, you may think that, not quite that, because this is after Marie Curie. For 100 years after her, there was one woman got it. And how many people know who it was? I'll come to it. Okay, I'll come to it. Many deserved it, of course, and it's to do with a more male-dominated culture of the 20th century. Not women's ability, obviously. So my message to young people was, don't be motivated to do science by the thinking you might get a Nobel Prize. Be motivated by it because you're enthusiastic, you love it, the joy of doing something, maybe finding something new. And it's fun, privileged to be part of it. And there are times when it'd be frustrating, even things don't work out, but get through it. So anyway, my message generally to young people is to find something you love to do, whether it's physics or biology or music or art or whatever it is, and just do it as well as you can, and maybe somebody will pay for it. So a kid said, well, I like to play video games. I said, well, learn how to make them, and then you can make a career out of it. So this was the first woman, the only woman who won a Nobel Prize in the period of 100 years in physics, Maria Goppert-Mayer. So she was born in 1906, died in 1972, got a Nobel Prize in 1963 for finding out the structure of atomic nuclei. Okay, so I hope, maybe you can't read it here, I can have a hard time to read it here, but she was a volunteer researcher at the University of Chicago. Her husband was on the faculty. She wasn't given a job. I don't know if it was because of nepotism policy that they didn't employ husbands and wives together, but anyway, she didn't get that. She was turned down at Columbia and at Johns Hopkins universities, but got a part-time job at Argonne National Lab near Chicago, which is part of the University of Chicago, or associated with it. In her spare time, she made this discovery about nuclear structure. That's a picture of her getting the Nobel Prize, walking in with the King of Sweden. And I had the luck to be attending one of these Nobel Prize ceremonies in Sweden when I was a professor there. And it was an amazing thing, everybody dressed up in their penguin suits and so on. The picture of do you know what she's holding, Maria Goppert-Mayer? How many people? Yeah, you know what she's holding, right? Slide rule, right? We used to use those before we had our little computers, slide rule. So she did all her calculations with slide rule, as we used to do. So you can't read those numbers in this table here, but it's about what we call magic numbers. So all the different nuclei in the periodic table, some are very stable, some are very unstable. And she realized that it depends on the number of protons and the number of neutrons. And the series of numbers here, 2, 8, 20, 28, 50, and so on. If a nucleus has those numbers, they tend to be very stable. Of protons, the same for neutrons. So if a nucleus has both the magic number of protons and neutrons, It's very stable, and you'll see some of them if they're in both those tables. Called magic. I just put this picture on here. Magic is real. Magic numbers are why are they? She figured out why the shell structure of the nucleus makes them real. About magic, I put a picture of me here meeting two magicians, Penn and Teller, and James Randi. That was at a conference in Las Vegas, our Committee of Skeptical Inquiry, which was a very interesting conference. I'm going there in October as well this year. Anyway, here's a table of the women Nobel laureates in different categories. You see on the left you have the Peace Prize. Many, many women get the Peace Prize. I added one on the right there, 2023. That is Nargis Mohammadi, and you probably can't read it, and I can't read it unless I turn around, but so for fight against women's rights. Okay. You can read it, okay. Thank you. And I put there in red 3 more recent ones since 2018. I gave this talk to my UU church back in Naperville 3 years ago, in 2019, so I updated it a bit. So times are changing because in the physics column there, you see Marie Curie and Mira Goppert-Meyer, and then 3 more recently than in 2018 and so on, and I'll talk a bit more about them. In 2019, there weren't no women in the Nobel Prize, but there was one woman on the committee. In fact, the committee was chaired by a woman then, who I happen to know. But times are changing, as I'll see, but maybe not fast enough. So going back in history now, here's a picture of Émilie Le Tonnelier de Breteuil de Châtelet in France. She was an aristocrat, high-born French lady. She married the Marquis de Châtelet, and lived in a castle there. She was a great friend of Voltaire, and she loved studying maths and physics. And then actually, Vernet Voltaire is near Geneva, and I lived there for a while. That's where Voltaire was. So she postulated a law of conservation of total energy, including kinetic energy. She translated Newton's Principia from English into French, and with a commentary about it. In fact, she found a correction to be made in the things. This is a dissertation about energy conservation. She wrote books on the Bible, on finance and so on, a really polymath. She predicted about infrared radiation, or heat radiation, and conservation energy, as I said, if you include kinetic energy. And that was proved much later by a great woman mathematician. Do you know who that was, about the conservation of energy? I think that's on my next slide, Emmy Noether. So that's her dates of birth and death. She was a mathematician, really, but she got into physics as well. And there's a lot of words here. Her father was a famous mathematician. I'm wondering if there's a gene for mathematics. She studied abstract algebra and other fields. So Emmy Noether worked for 7 years with no pay, being excluded from academic positions at that time. She was noticed and recruited to the University of Göttingen, but the faculty objected, so she didn't get a position there. Well, she went there and lectured under Professor Hilbert's name, without pay, but he let her lecture using his name as if doing it for him. At age 27, she got paid 37, as a private docent, which is a very lowly sort of position. In 33, being in Germany and being Jewish, all Jews were dismissed from universities by the Nazi government. She came to America then, to Bryn Mawr College, women's college there. And a couple of quotes about a former student of hers who said she was completely unegotistical and free of vanity and so on. And Einstein said she was the most significant mathematics genius thus far produced since the higher education of women. I wondered whether he put that in. Okay, whatever, think about that. But what she proved was This is so important. The relationship between conservation principles and symmetries. A symmetry is something where you change something and nothing changes. That's simply put. But if you do a physics experiment here and there, it doesn't matter where you are in space, the physics is the same. Okay, take away, I mean, if in a gravitational field, that's external, but physics doesn't depend on where you are. And she said that if this is true symmetry, then momentum must be conserved. So, two balls hit each other, or you hit, momentum is conserved. And similarly, if you do an experiment in physics, the results are the same no matter what time you do it. So physics is not dependent on time, that's a symmetry, then energy must be conserved. And another one is about angular momentum. If the physics doesn't depend on the orientation in space, then angular momentum must be conserved, which is why when a skater brings her arms in doing a pirouette, she spins up. That's angular momentum being conserved. It helps you ride bicycles and so on. These are very important relations between symmetry principle and conservation laws. And I put at the bottom there was a colloquium at Fermilab on the 100th years of her theorem. I put a link there to many of the colloquia at Fermilab that you can see on YouTube. There are hundreds of other outstanding talks on videos there. Moving on, Caroline Herschel. So Herschel, her brother, came to England as an astronomer. She joined him, and she did a lot of work, of course, just to help him, but she actually was a much better, in a way, observational astronomer. She discovered 8 comets. Now, things were all about comets then, these things, mysterious things, and she used telescopic observations and catalogued these nebulae, little clouds in the sky, looking for comets. She catalogued 2,500 of them. Only 100 were previously known. She got the gold medal of the Royal Astronomical Society. Now, it turned out that most of these weren't comets, they were nebulae, which wasn't known about cloud. Nebula means clouds. What were they? It was only later found out that they were actually most of them are distant galaxies. And there's another woman who helped figure that out. Next one, Mary Somerville. Those are dates very similar to Caroline Herschel. She was Scottish, studied maths as a girl in spite of her father, who said girls shouldn't do that. She married William Somerville, and then she hosted a sort of intellectual circle at a home, including Charles Babbage, who invented a computing engine, mechanical computer, and John Herschel, who was Caroline's nephew, actually, and William Herschel's son. So she had this circle at home, and she did experiments herself on magnetism and wrote about physics and astronomy. She translated from French to English Laplace's Mechanics, Mechanism of the Heavens, became a major textbook, and she was made an honorary member of the Royal Astronomical Society, together with Caroline Herschel, the two of them, the first 2 women members of that society. Moving on, Maria Mitchell, that's a picture of her there. She was an observational astronomer. She was the first female astronomer professor in the United States at Vassar College. Her father taught her to measure the position, star positions and so on. He did that to test the accuracy of navigation for sailors and so on. So at 17, she started her own school for girls, leading science and maths, and she discovered a comet which made her famous, actually, because that was a comet that became visible to the naked eye. So she also traveled 2,000 miles to see a total eclipse of the sun, so she was very serious about astronomy. Then we come to Marie Curie. Everybody knows about her because she got 2 Nobel Prizes, one in physics and one in chemistry. And her daughter, Irene, got a Nobel Prize as well, actually. She married Pierre Curie, that's her name. She was brought up in Poland. I've actually visited the house she lived in Warsaw. So she discovered elements, she discovered radioactivity. Before she was a private tutor. Her elder sister came to Paris and had priority, and she had to stay home and earn some money, but eventually she got to Paris and joined her sister. It was like a new world opened up for me, the world of science, which I was at last permitted to know in all liberty. So here's a picture, telling picture. It's the first Solvay conference in physics in 1927. 1920s were a very special decade for physics, and here I put the picture up because you see here all great physicists, and they're all men, all white men, I think, actually, and Marie Curie is there in the front row. I mean, she was treated as an equal by them. Of course, by then she'd already got the Nobel Prize. Actually, the Nobel Committee wanted to give it to Pierre Curie, and he said, I'm not accepting it by myself. Marie has to be part of it because she did most of the work actually on that. So he insisted that she get a share of the Nobel Prize, which she certainly deserved. Moving on, Henrietta Swan-Leavitt, astronomer. So she was hired to study, to help astronomers study stars and measure star brightnesses, especially variable stars, stars that vary in brightness periodically. In the middle there you see a graph of the brightness of a star, a particular type called Cepheid variables. And what she realized by measuring the periods of many stars at about the same distance from us in the Magellanic Clouds, that there was a relationship between the period of the star and its brightness. And you see a graph there showing how the period of the star, is it days, is it 10 days, 20 days, or whatever, depends on its brightness. Because they were all at about the same distance, that meant that they were all intrinsically about the same brightness. And this relationship enabled people to measure the distances to stars, even in another galaxy, right? By measuring the period, you knew their brightness, and if you knew their true brightness and their apparent brightness, you get the distance. So it was shown from her measurements that the Andromeda galaxy is actually very, very distant. It's not something local to the Milky Way. So that was critical for understanding the size of the universe, because before that, people thought maybe the Milky Way is the whole universe, that's it, right? Harriet Brooks, too many words here, I'm sorry about that, but she was a student of Ernest Rutherford, and he asked her to study so-called emanations, radioactivity, was it a gas, whatever it was, and she showed actually that beta rays, which were a radiation from radioactive substances, were the same thing as electrons that had been discovered by J.J. Thomson. And so these were electrons that we know as orbiting atoms actually came out of atomic nuclei. So that was measured decays of them and so on to discover new radioactive isotopes. So, but she was very modest. She said, I'm afraid I'm a terrible bungler in research work, but Rutherford was impressed by her work. And she was there was pressure for women in their 30s to marry and have children. But next, Lisa Meitner, a very famous case because she clearly should have got a Nobel Prize in physics, but she didn't get one. She discovered nuclear fission, actually. So she was working in Germany with a chemist. There's 3 pictures of her in 1906 to later. And the chemist she worked with was puzzled because he's a radiochemist, and he found barium together with uranium, and couldn't understand what that was doing. But being Jewish, she had to escape from Germany. She went to Sweden, where she was hired by Manus Siegbahn, but he treated her as a junior assistant. I think he was jealous of her. She was already obviously done brilliant work. But then there was this puzzle of Otto Frisch, who was a radiochemist, and she was on a walk with it was Hahn was the chemist. Otto Frisch was her nephew, and she was on a walk in Sweden with her nephew, talking about this. He was a physicist too, and she realized what was happening was that the uranium nucleus was being split in two, and as it was split in two, releasing some neutrons together with energy. So this was a discovery of nuclear fission, okay? And that was what led, of course, to the development of the atomic bomb. She refused to work on that. She and the Nobel Prize in Chemistry was given to Hahn. She was not included in that. And we think it was because Manas Sigban was jealous of her. He didn't want her to get this sort of recognition because she'd been sort of junior. He gave her a junior position in his group. So that was a clear miscarriage of adjustment. But Vera Rubin, okay, she discovered. So there's pictures of her, a woman's place in the dome. So Vera Rubin discovered dark matter. Okay, what she did was she measured the rotation curves of galaxies. Now, how do you do that? You see a picture of a galaxy like the Andromeda Galaxy, and the stars on one side, the spectral lines shifted slightly to the red, on the other side slightly to the blue. And it's a Doppler shift. When things are coming towards you, the light looks bluer, going away from you looks redder. And by measuring that on different galaxies, she showed that actually the Andromeda Galaxy rotates. It takes 30,000 years or so to go once round, but these are rotating. And then when you calculate the rotation of these galaxies, the speed of rotation is a function of distance from the center of the galaxy, because they're not solids, of course. You find they follow a relationship showing there's more mass than there is in gas and dust and stars and planets. So that's missing mass, and it's now called dark matter, and we don't know what it is. We think it's made of particles we haven't yet discovered, but it's stuff that has gravity. So that's what. Now, Vera Rubin did not get the Nobel Prize for that great discovery, but at least she's now, she gets credit. She got a gold medal of the Royal Astronomical Society, but not a Nobel Prize. Okay. Joycelyn Bell Burnell, another one, who was actually just a student in England, working for a radio astronomer at Cambridge, and she noticed in the signals from the sky that there was something like pulses, like little pulses. And what was it? It was very peculiar, and she showed that actually it couldn't be local or something nearby. It was actually distant in the sky. She showed it, so then she told her boss about it. Of course, Anthony Hewish and Ryle, another astronomer, they got the Nobel Prize for this discovery. It was hers, but okay, he was a supervisor, and she was just a student. She's gone on to become, very well known and so on, but she got a special breakthrough prize in 2018, and she's donating it to help women and ethnic minorities and refugee students become physicists. Now, what she discovered was a pulsar, which is a collapsed star that's spinning at very high speed. Some of them are spinning 20, 50 times a second, radiating these pulses of light and radio waves. There's one in the center of this picture, the Crab Nebula, which is the remnant of a supernova that was seen by the Chinese back in around when, I forget when it was, 1054. Okay, and that's a remnant of this. And in the middle of that is this spinning pulsar that's emitting light flashes and radio flashes as well. Nancy Roman, she got a PhD in Chicago, and she's a mother of the Hubble telescope. Now, before that, Spitzer had proposed a dream talking about the advantages of an observatory in space, because you get above the atmosphere and so on and see. But the Hubble Space Telescope was his dream, and she actually led that, organized and convinced Congress to build the Hubble Space Telescope. And the Hubble Space Telescope, well, this is an amazing thing pictured. This is looking at a piece of the sky that's about the size of a grain of sand at arm's length. And you look in a part of the sky where there are no stars in our galaxy, so you're looking beyond our galaxy and taking an exposure of, I don't know how many hours this is, like 100 hours exposure on this extremely sensitive thing. And every dot there is a galaxy, a distant galaxy. So that when you realize that that's a tiny part of the sky, and it's pretty uniform all over the sky, so there's about 100,000 million galaxies in the visible universe. Think of that when actually we only knew about one when my father was born, actually. Moving on, Donna Strickland. So at last we get now a Nobel Prize in 2018 for a woman. That broke the desert, if you like. That's her. She attended McMaster University. She was one of 3 women in class of 25, very typical. While a graduate student, she found a way to make ultra-short laser pulses, which led to her getting the Nobel Prize. And her daughter Hannah is a graduate student in astrophysics. So she figured out a way to make extremely short pulses of light, ultraviolet light, fast pulses. And
Let's use a hand mic.
oh yeah, okay.
If you're broadcasting this on Zoom, you need
Yes, I need that. Okay, thank you. That works better. Good. Okay, thank you, Sterling. Okay. So she applied for a full professorship after she was awarded the Nobel Prize, and she got it at the University of Waterloo. She was the first full-time woman professor there at Waterloo. More recently, now in 2020, so a year after I gave this talk at my previous church, earlier version, Andrea Ghez got it. So she was the 4th woman Nobel Prize in Physics, born in New York City, 65. She was inspired by the Apollo moon landings when she was a little girl and wanted to become an astronaut. Her mother bought her a telescope, encouraged her, and she got a BS in physics at MIT, Caltech in astronomy. So what she's worked on, of course with a team, but she was pushing this. The picture on the right, you see, looking towards the center of our Milky Way galaxy, you see many stars there. If you look at the tiny square in the middle, blown up, that cross shows the center of our Milky Way galaxy, and there's a black hole there with a huge mass, a few 100 million star masses in that black hole. And around that you see those little dots, white dots, are stars, images of stars close to the black hole in the center of the galaxy. And they're visibly moving around. There's one that's particular one called S2. It's got a 16-year orbit, elliptical orbit. The star's traveling around the center, this black hole in the center of the Milky Way galaxy at 7,650 kilometers a second. Okay, so that's like 5,000 kilometers a second, which is a great test of general relativity, but it enabled to measure the mass of this black hole in the center of the galaxy. So she got the Nobel Prize for that, together with a couple of male physicists about the properties of black holes in the center of galaxies. Moving on, now most recently, last year actually, Anne L'Huillier got the Nobel Prize shared with 2 men. She brought it for techniques of compressing light signals to extremely tiny attosecond signals. An attosecond is 10 to the minus 18 seconds. That's 18 zeros seconds. So this is enabling you to actually measure the motions of electrons in atomic materials, in atoms and so on. And there's a scale here, attosecond on the left, heartbeat of 1 second in the middle, and the age of the universe on the right. It's a log scale, of course, from 10 to the minus 18 seconds to 10 to the plus 33 seconds, whatever. So moving on, now there are many amazing women in STEL, of course, far too many to mention, but I just mentioned a couple here. Dr. Gabriela Gonzalez. So she's a spokesperson for LIGO. LIGO stands for Laser Interferometry Gravitational Wave Observatory. It's an amazing project where you have 2 vacuum tube arms at 90 degrees to each other, 4 kilometers long. You send light along each one, reflect it from the back, and from the interference of the light coming back to the center, you can actually measure displacements of the mirrors at the ends of these arms, not just the size of a nucleus, but even smaller than an atomic nucleus. And it's amazing how that can happen. But they detect shakings of this, actually gravitational waves, which are distortions in space-time coming from objects with like orbiting black holes spiraling together and merging. And this was how gravitational waves have been used now as observing. When you open a new window of the sky, you see more amazing things, including neutron stars colliding with black holes and so on. So she's in charge of, she's a spokesperson for this project. Then Fiona Harrison is leader of another telescope array studying supernova remnants and so on. The picture on the left is an X-ray source in a distant galaxy studying these things. Now, here, another change or sign of a change. Fabiola Gianotti is the Director General of CERN, this lab in Geneva where I'm still working there. There's about 10,000 physicists from all over the world working there. CERN itself is the host of this place. I was there for 18 years. And so she was actually spokesperson of one of the two big experiments at the Large Hadron Collider, colliding protons on protons at the highest energies we have anywhere in a controlled fashion. And they discovered the Higgs boson, ATLAS, and CMS, the other one that I happen to be on. Fermilab is part of CMS. So she was spokesperson of that ATLAS project at that time, and now she's Director General of CERN. And so I can quote from her. She said, "I cannot say myself that I ever felt discriminated against. Perhaps I was, but I didn't realize it. But she's helping break down barriers the male-dominated field created for aspiring female scientists. She specifically wants to give women more support when having children. She never had children herself. She was too busy, a decision she now regrets." So about the discoveries of the top quark at Fermilab and the Higgs boson at CERN. So these were huge endeavors, the discoveries of many, many, many physicists. For example, the top quark at Fermilab, the project I was on, we were 550, 600 physicists working on that. And the Higgs boson was even more because these two big projects with 3,000 physicists on, and the physics prize can only be given to 3 individuals. So you can't put the discovery on any particular 2 or 3 people, but the Higgs boson got the Nobel Prize because of its prediction by Peter Higgs and others. But I have a comment here because the Nobel Peace Prize is often given to organizations, not individuals. And so I suggested that Fermilab and CERN could be given the Nobel Prize for Peace because it's fostered international collaboration by CERN. Physicists from all over the world working together. It's a subject, we can work together, it's universal. And I had a talk about, a column about this, Peace on Earth and Goodwill to All. That was in 2018. I quote, "What you may be thinking, I thought this was a science column. What has science to do with peace? Those who visit Fermilab or CERN, the European Laboratory for Particle Physics in Switzerland, understand that today many international scientific organizations are at least partly inspired by CERN's success. What happened later was that Russia invaded Ukraine, and that caused a huge problem, actually, because we have to keep collaborating with the Russians and everybody. And there are many Russians working at CERN, as well as Ukrainians. Of course, they're not responsible for what Putin did there, but still, the labs that were supporting them had to support the government. Anyway, it was a big mess. So I checked in the last 10 years, from 2014 to 2023, the Physics Nobel Prize was getting 25 men and 2 women. It's about even less than half of the course because the number of women in research in physics in this country is about 23%. And there's every year an International Day of Women and Girls in Science. It's on February the 11th each year, so remember about that. Other good news, I put that Mate launched an astrophysicist Barbie in 2019 to inspire girls in STEM. And Barbie has had over 200 different careers. I just checked and looked at some of them. These are some of Barbie's careers, because all in the kitchen. And there are other careers, of course, too, but there's so many. But the times are changing, maybe not quickly enough. I think actually the divergence between boys and girls happens already in schools, where boys seem to gravitate more towards the physical sciences and girls towards maybe the softer sciences. So it takes a long time to change that culture. It's changing, but very, very slowly, as you see. Thank you. So I'm now open for questions and comments. Please wait for the microphone if you have a question, because it's being recorded. And I think this will be posted on YouTube like the other ones we do. Any questions or comments? Yes, sir.
Are you going around any Are you going around to any schools with this, presenting this talk?
Thank you. That's a good idea. I haven't been to schools for this talk, actually, but that's a very good idea to do that. So if any schools, I'll certainly be welcome to give them. I did back in 2005, which was the World Year of Physics, because 100 years since Einstein's great year, and I was on an organization at Fermilab, Friends for Science Education, and we got together and set up a program where schools could ask Fermilab to send a scientist out to give them kids talks and demonstrations, and we did that, and we reached 10,000 kids in their schools that year, and it's continued on. So we've now reached over 200,000 kids in their schools. But we go to middle schools mainly and give them science shows, you know. They can do electricity, magnetism, gravity, whatever, just to show them, you know, it's fun. But to give this talk at schools, yeah, I'd be willing to do that if I should think about doing that. I'm happy to do that, yeah. Good idea. Any other comments?
I'm a little afraid to ask this. Have you heard of Sabine Hossenfelder? Hossenfelder? Oh, I don't want to. She has a YouTube channel. Okay.
Yes, I do. That was just my memory. Sabine, yes, she has a, so check it. Sabine, second name is? Hossenfelder. So she does a lot of great science talks every month or more often maybe. Yeah, many of us are actually. So here's about bigger colliders. So the collider at Fermilab was the highest energy collisions of particles anywhere for nearly 25 years. At Fermilab, I came over here to work on that, colliding protons and antiprotons. And it was a 4-mile around ring of magnets. That was closed down because of the CERN's Large Hadron Collider, which is 16 miles around with stronger magnets and gets to 7 times higher energy. And then, so people, what's the next step? Okay, and CERN has designed and working on a ring that is about 90 kilometers around, goes under the mountains, of course, under the lake, and to get up to about 6 times higher energy. And people give whole talks about how exciting this is because, you know, but, I mean, the thing is, well, the last really fundamental discovery of the Higgs boson at CERN in 2012, since then we haven't discovered a new particle, a new fundamental particle, many new composite particles, and doing so many experiments there, there's 100 papers a year come out, and many of them are, we search for this, we search for this, we search for this. We didn't find it. That's not a failure if it's not there. It would be a failure if it was there and you missed it. But by that, because theorists we know there's missing things. We know there's dark matter, we don't know what it is. Dark energy, we don't know what it is. There's many things we don't know what they are, right? But when you find that something's not there, that's progress because you're limiting the possibilities.
So the question is dark matter necessarily a particle?
That's also a good question. Probably 98% of physicists will say they think it must be a new particle because all fields seem to have particles that go with them. A particle that we haven't yet found because either it's too massive to be produced at the Large Hadron Collider or it's too weakly interacting to be produced with enough to see. Actually, what project I'm working on now is the idea that there are particles that are being produced, but they're so weakly interacting that we haven't found them yet. But that's another story. But maybe, I mean, theorists have so many ideas, and we're trying to restrict the possibilities. And one possibility is that they are partners to the neutrino, which are very, very light particles, that these very massive partners. But maybe that's not right. So could it have to be a particle? Conceivably, it may not be a particle, but a field that doesn't have a particle. But all the fields we know seem to have particles that go with them. Gravity, maybe not. Maybe that's different. If the gravity's got a particle, it's so weakly interactive, we haven't got a chance of ever detecting it as a particle. And then there's dark energy. What's dark energy? Does it have a particle that goes with it? I have ideas about that. I think We can talk about that, because if dark energy has particles that goes with it, they've got very strange properties. I think there may be tachyons that travel faster than the speed of light, but that's another story. Okay, so it doesn't. Most people think it must be a particle we haven't found yet, but if it's these ultralight neutrinos, they're probably too massive. Sorry, if it's a partner to the ultralight neutrinos, but a very heavy one, then it could be that we won't find them at the Large Hadron Collider, even the bigger one, even. So it's a whole question. How far should we, how far do we go? Well, here's one thing. When the money that's spent for this field goes into pushing technology, to advance technology. For example, the World Wide Web, which we all use, was developed at CERN for communicating and sharing data between particle physics experiments. When you go for an MRI scan using superconducting magnets, those were developed largely by scientists wanting to have stronger magnets for this sort of project. There's so many spin-offs, medical imaging and so on. So the spin-offs are there. So if you said we don't stop spending money on these big projects, spend it on other, it's competition, right? But I think in one sense this is worth it for bringing scientists and people of all nations together, working together in collaboration. So that's, I call it science for peace, but whatever, it's a big discussion. David, did you want to say something about that?
I wanted you, please, to expand on this question of antipathy or resistance to investment in larger accelerators.
Okay, well, I can give one story, which was I was at CERN, and there was a movement among other scientists in Britain to say, CERN is costing us too much, we should pull out of CERN, if there's international collaboration and so on. And they set up, so the government did a study of this. Margaret Thatcher was actually Prime Minister at the time, and she was a chemist she got a chemistry degree and so on. But these people thought that if we stopped spending that money on CERN, they would get that money for their own research. It wouldn't have happened. The money would have been kept by the government. It was a separate sort of pot of money. So it's a mistake to think that if we stop spending money on this expensive particle physics, then that would benefit others. By the way, Fermilab costs about $1 per person in the USA, $1 per year. Okay, so that's a sort of scale. So, and yet Fermilab, people from all over the world come and collaborate there, you see. So for international collaboration is an aspect of it. So you can't. Now, when Fermilab was being proposed, Robert Wilson, there's a congressional hearings about it, and somebody said to Robert, what's this project got to do with the defense of our country? Which was spending a lot more money, of course. He said, nothing. Really? Nothing to do with the defense of the country? Nothing except to make it a country worth defending. Which is quite a clever answer, actually. Because we do this. We advance science. And because of the developments in pure science that, of this sort, also, the space telescopes on James Webb, which we'll have another talk about soon, I think. This money it comes into not only comes into the economy, but it also benefits everybody, I think. There were other questions around here, so.
Well, it's just an observation, and maybe I just wanted to make it. There's discrimination against women, yes, but science is incredibly competitive. I don't know that, people think that people go at this just for the improved human knowledge. But I've watched two physicists nearly come to blows over whose paper it was and who deserved the authorship. And I suspect you too have seen this competitiveness. So it's not just women that get discriminated against. There's all sorts of competition going on in science. And I don't think the general public realizes how competitive it really is.
That's a very interesting comment. My daughter, actually, she did a master's in cultural anthropology, and she decided to take a subject, I don't know why, about competition and collaboration in our field of particle physics. Because we build these huge things. I mean, these experiments I'm working on at CERN, 3,000 physicists from all over the world, engineers, working together to get this so complicated thing together. You have to collaborate, absolutely. Now, on the other hand, there's competition at every level. You have a small university group with a professor and some graduate students. The graduate students want to get a job after their PhD or whatever, so they're competing, but they have to collaborate together. If you're a bad collaborator in this field, you probably won't last long. But that doesn't mean there's not competition, but there's somehow in some sort of balance. And I think that it'd be great if other enterprises around the world could learn how to collaborate and put competition, it's there, of course it's there, but they come together. So we have, so there's competition between Fermilab and CERN. There's competition between the two big experiments at CERN, the bigger one, Atlas and CMS. There was competition, but there's collaboration too. So, for example, when one is coming up, they think they're coming up with something very interesting, the others know about, they collaborate and compete at the same time, and it's an interesting balance that you have, and it would be good if that sort of balance happened elsewhere in the world, but science, because it's apolitical, apart from wanting to get money from governments and so on, but and we don't talk about divisive things like religion and so on, so yeah. But yeah. Yeah, there is that. You see, it's a different field. When we have, I mean, if you're in some fields where a group of half a dozen people work together on a thing, and then who should be the first named author on the paper and so on. Now, we've had big discussions about authorship of our papers because when you have 3,000 physicists on a project, you know, so the decision has been made to put all 3,000 on the author list. So don't look at how many papers I'm a co-author of. It's over 1,000 papers, but many, you know, it doesn't matter. When you apply for a job, as you've got a PhD, you apply for a job. I mean, I don't care how many papers you're a co-author of. Which one did you actually do yourself? Which was your thing? And your other, you know, your colleagues know so as well. And you know, but I've seen very strong competitions between Carlo Rubbia, who was the leader of my experiment I was on at CERN, discovering the W and Z bosons, and the other team, so he was extremely competitive, and when I joined that project, after the W and Z had been found, but he hadn't yet got his Nobel Prize, that was so tense, so difficult. He was a very difficult person actually, because he was so domineering, you know, and it was a shock for me, because my previous experiment, we were about 60 or 70 people, and we all collaborating, no big egos and so on. And then I joined that bigger experiment where he was the boss, and he had a sort of divide and rule. You don't talk to him, you work on that, you work on that. He wanted to be the only one, the spider in the middle of the web sort of thing. But there was competition between him and another experiment that found the W and Z at the same time, but it had been Carlo Rubbia's idea. He got the Nobel Prize, and the leader of the other experiment did not, but he was very generous about it. He was a great man, actually. And he said, yeah, it was Carlo Rubbia's idea, and he got it started, so he deserved that. But they were, you know, it's a tension, right? But, yeah. Sorry.
Yeah, so I'd like to re-ask his question, which is, what's the objection to building a larger collider?
The money.
Well, the objection, well, I think we know there are particles we haven't found yet. We know there's matter we don't understand yet. It would be really, really valuable to understand. We need to understand matter. But maybe the dark matter particles are much more massive than wouldn't even be found at this extension one. So we could build this extension one 5 times more energy, right? So we could still not find the dark matter particles. Yeah, that's the main objection, I think.
Since I brought it up, I'll continue. That's actually Sabine Hassenfelder's criticism, that they haven't found more particles in such a long time. And the papers that are coming out are literally saying, we looked for this was predicted, we didn't find it, we didn't find it, we didn't find it. And what's happening is so many physicists are going into this field, and it's sucking the brain power from what could be done outside of particle physics. That's her criticism.
I could personal comment on that. If I have a young person asking me for advice, he's got a physics degree, wants to do a PhD, which field of physics should he go in? Don't repeat this outside, but I would say I'd go into astronomy or some other field that is you're not one part in 3,000 physicists where we don't even know each other. I go to a meeting, at CERN of this project, and there's 3,000 people in the project. Maybe 1,000 of them are online and 500 of them in the room, and I look around and I don't know many of them, but then I'm older than all of them. But it is a lot of competition, because if you're a graduate student doing a PhD, you know that only about a third or a quarter of you can actually go on to a postdoc position. So there's competition. And I haven't seen it lead to fisticuffs or, really nasty things. Because if you are not a good collaborator, you're probably not going to get a job. If you have a reputation when you apply for a postdoc position as being a difficult person or somebody who doesn't work well with others, I wouldn't hire them. So I think you have to learn to collaborate, even though you really want to get that job. So they work very hard, harder than I did in those days, but to get ahead.
Yeah, thank you, Mike, thank you for your presentation. And I think the topic is so important in having us learn about, we don't necessarily know about all the women that came before us. And great for young girls, and to see what kinds of opportunities are there. And I think what you were just saying was so important about collaboration and talking to young people about the importance of teamwork. Not just, of course, in physics, but in all things, but just so important, more than, but I guess to hear someone like you say that at this level of science, how important it is to be able to work with other people on a team is really great for students to hear, I think. Great message.
Yeah, thank you. Yeah, so I think, and I like your opinions on it, I think the divergence with, I think all kids probably, when they're 8, 9, 10, they're fascinated by science. A lot of them like stars and astronomy. But somehow, by the time they get to 13, 14 years old, there's a divergence, and girls tend to be more encouraged to biology if they're scientifically interested, or softer sciences, and I think physics is for boys more. And if that's the case, you get this splitting, because by the time you get to PhDs, at least in our country, there's about 20% of women only. But we're trying to change that. We have, at every meeting, we talk about diversity, equity, inclusion, and so on. But you can't change something on that time scale. Actually, I've got one slide which is perhaps interesting on the next, and a backup about this. Okay, well, 2 slides about, this is at Fermilab, about gender. You see here, different categories. Postdocs, 25% female. Scientists, 17%. Mission support, 50%. That's a Fermilab. That was in 2018. But this one I thought interesting. It came out for the International Day of Women and Girls in Science, I think 3 years ago or so. And in those countries, more than 50% of scientists and engineers are women. Lithuania, Bulgaria, Latvia, Portugal, and Denmark. Interesting, okay? More than 50% of the scientists and engineers are women in those countries. Now, presumably it comes back to culture in schools and so on, I think. Because And I'm not saying I think that there should be 50% women and men, but I think that all girls should be encouraged to do what they want to do, you know, and given the opportunity, and not told, you know, physics is a thing for boys and girls should do. Have you seen chemistry, lessons in chemistry? That's a great, lessons in chemistry, okay. It's a very interesting novel about girl chemists and cooking and stuff. Any more comments? Oh, yeah? Anybody? So, what can be done? I mean, what should be done? I mean, you can't change 25% up to 40% overnight, but somehow schools should be encouraging it. The idea of giving a talk like this at schools would perhaps be helpful. I'm certainly willing to do that. Okay, maybe that's it. Thank you all for listening. Thank you.